Hello everyone. Thank you for the opportunity to present some of the key findings from my research on rare earth elements in alkaline lakes of the East African Rift. My name is Lukas Klose and I'm a postdoctoral researcher at Constructor University in Bremen. And before I begin, I would like to acknowledge my colleagues, Timo Kreitzmann, Lydia Olaka, Moses Misongo, and Michael Bau, who contributed significantly also to this project. Sorry. So why are we interested in studying alkaline lakes and especially those from the East African Rift? Alkaline lakes or soda lakes are predominantly found in arid region and geologically active zones like the East African Rift Valley and are unique geochemical environments which occur throughout Earth's history. Characterized by high sodium and carbonate content, these lakes exhibit pH values above 9 and varying salinity levels. And despite these harsh conditions, they support diverse microbial life, making them the most productive aquatic ecosystems that we know of. Moreover, they were proposed to serve as modern analogs for Precambrian seawater and could help address the phosphorus problem related to the origin of life. However, these lakes face increasing threats by anthropogenic activities due to their presence in hydrologically closed basins. And what do we know about rare earth element in these alkaline lake environments? So in general, the aquatic behavior of rare earth elements in most surface waters is governed by the complexation with organic or inorganic ligands, and that is especially true in neutral to alkaline waters. And there's a surprisingly limited number of studies that actually analyze rare earth elements in these alkaline lake environments. But all of them describe two characteristic features for the rare earth element distribution in these lake waters. One is distinct heavy rare earth element enrichment over light rare earth elements, and the second is this pronounced positive serum anomaly that you can see here. And both features have been previously attributed to the complexation by carbonate, as the bicarbonate complex has an increasing stability constants from lanthanum to lutetium, so higher solubility, that describes this heavy rare earth element enrichment. And the positive serum anomaly has been attributed to the oxidation of cerium-3 to cerium-4, and then the stabilization of a higher order cerium-4 carbonate complex in the lake water. However, there's obviously one example that always falls out of something, and that is in this case Mono Lake in the US, that although it shows this heavy rare earth element enrichment over light rare earth element, it lacks this clear positive serum anomaly that is so characteristic for most of the other alkaline lakes that have been analyzed. And previous researchers proposed that this lack of serum anomaly or this missing serum anomaly is associated with the especially high dissolved organic carbon of Mono Lake that is around 90 milligrams per liter. And this high DOC leads to a kind of a masking effect of the development of a serum anomaly. So this raises the question: in alkaline lake systems rich in dissolved organic carbon, is the rare earth element speciation dominated by the organic or the inorganic? In the alkaline lakes, mostly carbonate dominated, so these are the dominating ligands. And understanding the speciation of the rare earth elements could advance our knowledge on orthogenic mineral formation in both the current and the ancient lake environments that occur throughout history. So our focus shifted to the East African Rift alkaline lakes because they are known for having high dissolved organic carbon concentrations, but the amount of rare earth element data for the lake waters was previously rather limited. So this is why during two sampling campaigns in September 2023 and June 2024, water samples were collected from 8 lakes in the Kenyan part of the East African Rift Valley. And these equatorial lakes experience semi-arid climates where evaporation exceeds the precipitation. And northwest-southeast trending faults lead to a segmentation of the region into distinct drainage basins that also influence the lake hydrology and composition. So where the basins are hydrologically open, such as here at Lake Naivasha, Lake Noloiden, Lake 92, and Lake Baringo and Lake Kamnarok, we have these alkaline freshwater lakes, whereas in basins that are hydrologically closed, such as Lake Sonachi, Lake Elementaita, and Lake Bogoria, we form saline alkaline lakes. And just as for completeness and for general understanding, I want to talk briefly about the major element compositions. So all our samples exhibited alkaline pH values from 7.4 to 9.9, and they were positively correlated with the electrical conductivity. On the right-hand side, you can see a Piper diagram showing not only our data, but also literature data, always illustrated in these diamonds. And we can clearly see that investigated lakes fall into two distinct groups. So we have these alkaline freshwater lakes that have low electrical conductivity of 90 to 660 microsiemens, total alkalinity of up to 5.95 milliequivalents, and DOC up to 18.8 milligrams per liter. And then we have the saline alkaline lakes that have significantly higher electrical conductivity of up to 32.9 millisiemens, total alkalinity of up to 461 milliequivalents per liter, and DOC up to 98.6 milligrams per liter. And now finally, shown on this slide are the rare earth element distributions of the investigated lakes, and also the previously available literature data. So in general, all rare earth element patterns that you see here have been normalized to post-Archean Australian shale, or PARS. And furthermore, all samples show a negative europium anomaly, which is likely inherited by the widespread occurring alkaline volcanic rocks of the lake's drainage basin. This negative europium anomaly can be rather small, here in the case of Lake Baringo, but this is kind of a normalization artifact. So if we normalize all these waters to, for example, chondrite, we can see a really clear negative europium anomaly. The total concentration of rare earth elements in these lakes range between 0.2 to 93 micrograms per kilograms, and only Lake Naivasha, Lake Bogoria holds significantly higher concentrations of up to 348 micrograms per kilogram. So staying on the left-hand side on this figure A, I want to show you the results for the saline alkaline lakes, Lake Sonachi in yellow, Lake Elementaita in orange, and Lake Bogoria in red, and also the literature data for Lake Bogoria. So samples from Lake Sonachi in yellow and Bogoria have been collected during both sampling campaigns, and they show a good reproducibility. And interestingly, the saline alkaline lakes, despite following this classic feature of heavy rare earth element over light rare earth element enrichment, they, similar to monolake, do not show this positive serum anomaly. At Lake Bogoria, if we compare the data from Kerich et al. From 2002, we can see that our data is approximately 5 times lower compared to the previously published data. And in Kerich's data, they also have this negative serum anomaly, which we attribute to the use of a larger membrane filter size in this data. So they use 0.45 micrometers, and possibly then the influence of autogenic particles or colloids that are smaller than this membrane size. We look at the PARS normalized ray patterns for the alkaline freshwater lakes now. So this is B, C, and D. And we first look at Lake Baringo, shown in purple here. We can see that the rare earth element patterns from the 2023 campaign, which are the circles here, and the 2024 campaigns, which are the squares here, are very different, both in the shape of the pattern, but also in the absolute concentration. And we attribute this difference to a higher influence of heterogeneous nanoparticles in the 2024 campaign at Lake Baringo, whereas in 2023, these heterogeneous nanoparticles were less pronounced. And this is supported by a similar rare earth element concentration and distribution pattern of the nearby Lake 92 that was also collected in 2024. So we would argue that the sample collected in 2023 is more realistic or more representative of the dissolved or not particle-bound rare earth element concentration. And if we compare this data from our data with the one that was previously reported by Taritz et al., then we see that these rare earth element concentration and patterns are in the same order of magnitude, but compared to the previously published data, our data is much more, the pattern is much smoother and more coherent, whereas previously published data was more zigzaggy and raises concerns about the analytical quality. If we look now at Lake Naivasha, we can see that the previously published data is in the same order of magnitude as the one that's we produced. The difference in concentration and shape, especially for the light rare earth elements, is also or most likely related to the use of different filter sizes. While the previous data from Ojiyambo was filtered through 0.8 micrometer filters, our samples was again filtered through 0.2 micrometer filters. And lastly, the patterns from Lake Oloiden here in green and Lake Kamnarok show, in addition to this slight heavy over light rare earth element enrichment, this and the negative europium anomaly, these clearly visible negative cerium anomalies, and this suggests that the cerium is affected by oxidative scavenging in these lakes, which is a common feature observed in surface waters. So as I've already mentioned, previous studies on alkaline lakes argued that the rare earth elements are controlled by the complexation with carbonates, which produce these characteristic heavy rare earth element enrichment. And simplified, this heavy rare earth element enrichment can be expressed by the shale normalized praseodymium over ytterbium ratio. So if we put the data that we produce from the East African Rift Valley lakes into a global context, and we compare it to the previously published data of rare earth elements by plotting the total alkalinity versus the shale normalized praseodymium ytterbium ratio, then we can see that increasing total alkalinity leads to a decreasing in the praseodymium ytterbium ratio, which means that there's a stronger heavy rare earth element enrichment in the water sample. And this is consistent with the increasing stability constants of the decarbonate complex from the light to the heavy rare earth elements. And that was also previously proposed by inorganic speciation calculations.
Yeah, Lukas, 2 minutes remaining.
Yes, thank you. But since the saline alkaline lakes from Kenya showed high concentrations of DOC, similar to Mono Lake, we performed a series of rare earth element speciation calculations by also accounting for not only for the inorganic, but also for the organic complexes. And due to time constraints, I won't go into details, but feel free to ask me later. But the important point from these speciation calculation is that the rare earth element speciation, even at high DOC concentration, is still dominated by carbonate complexes, which means or which further corroborates the results of previous work that carbonates play the most important role in developing these heavy rare earth element enriched patterns. And to further add to this, I've also added and plotted some samples from hyperalkaline cold springs that have a pH of around 11 from the Ronda peridotite in Spain. And you can see that high pH alone does not lead to this heavy rare earth element enrichment, but you really do need these strong complexing carbonate complexes to fractionate the heavy from the light rare earth elements. So to conclude, With our study on saline and freshwater alkaline lakes from the East African Rift, we greatly extended and I would say also improved the available data for rare earth elements, both within the East African Rift, but also globally. And furthermore, despite the high DOC concentration in these systems, we corroborate previous results that rare earth elements are predominantly complex bicarbonate. And to our knowledge, the rare earth element in saline alkaline lakes from Kenya are the only other systems other than mono lakes where we do not see this positive serum anomaly. And it seems that, like previous researchers already proposed, is that the high concentration of dissolved organic carbon has an influence on the development or absence of a serum anomaly in these systems. On the right side, you can see a plot again, total alkalinity versus the serum anomaly. We can see that, and the samples are color-coded based on, if available, DOC concentration. And you can see that increasing alkalinity leads in some samples to this pronounced positive serum anomaly, and in other samples that have high DOC to no or if only a very small positive serum anomaly. So with the presently available data, we cannot fully resolve the serum systematics in alkaline lakes, which clearly demonstrates the need for further research in these systems. And with that, I'm finished with my talk. Thank you for your attention, and take any questions that you have. Thank you.
Thank you, Lucas. We have some time for one or two questions, maybe one.
Yeah, I would
Yes,
have one
Sasha?
question if no one else has one. So I actually two questions. Can you say a little bit about like what the economic potential for rare earth elements is, and how would one exploit that or use that, or what the strategy in that direction? That would be the first question. And the second question is, you had surveys in June and in September. I was wondering a little bit about seasonality of results. Did you also have samples in, I don't know, February or March?
Yeah, so thank you for these questions. I think in terms of economics, I think the lake water itself is not, it would be not economically feasible because the concentrations in the lake water is not high enough. Even in Lake Bogoria, which has this 346 micrograms per kilogram. With the maybe it could be different in the suspended in the particles in the sediments, but all these lakes or most of the lakes are national parks. So these are in Kenya. These are all protected areas. The second question with regards to the seasonality. So both were sampled in the dry season. So far we do not have data or samples from the rainy season. But obviously I would expect an influence from the rainy season. What we do see from the major chemical composition is that during the last 10 years or so, 10, 15 years, there has been it was significantly wetter, so much more rain, and also that we see in the major compositions that our samples are more dilute compared to the previous data for major composition. It goes back to the 1960s. So in that sense, they are very well studied lakes, but just not in the sense of rare earth elements. Good. Thanks. Thanks.
Thanks, Lucas. We'll take one more, and then the other one we can put in the chat so that we can be able to finish in time. John Blandy?
Yes, thank you. That was very interesting. I'd like to ask Lucas, how important is the bedrock geology in the catchment in terms of the supply of rare earths? Presumably, they all come from peralkaline volcanic tuffs and other volcanic rock types.
Yeah, thank you for the question. I think that the more important is the complexation. So, I mean, these alkaline lakes do tend to follow in areas where we have these alkaline volcanic rocks there, right? So we need this. We need the theory of Oyster with the theory of chemical divides. So we need to have more carbonate than calcium in the beginning. Otherwise, we do not form the alkaline soda lake, right? We form maybe a calcium sulfate lake or a sodium chloride lake, right? So in that sense, obviously, the bedrock is fundamental in order to form the alkaline lake. But then the rare earth element distribution in the lake water is, I think, rather controlled by the stability of the ligands or the complexing ligands of the rare earth elements, and not necessarily by the rocks, because the rocks tend to have, on a chondrite normalized basis, light rare earth element enrichment over heavies. So they do not mirror the rock in that sense, the lakes, but there's a fractionation going on because of the stability constants of the ligands.
Okay, thanks.